In today's episode, 19-year-old Liz Rice loses her laptop in Paris before a critical presentation.
I got a taxi, I got out of the taxi, and then I wondered where I'd put that laptop.
But that doesn't discourage her from becoming a major eBPF contributor.
And we can change the kernel's behavior either to optimize it for a particular circumstance or do security.
And transform the way we do container network and kernel security and observability.
So we can do this kind of shortcutting for packets both ingress and egress. And the net result of this is no performance overhead in container networking.
Welcome to Cisco Tech Stories, a podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan.
Welcome to Cisco Tech Stories. This is part one of a special two-part mini-series exploring isovalent, Cilium, and Tetragon, and of course the technology at the center of it all, eBPF.
In this first episode, we're joined by Liz Rice, one of the most respected voices in the eBPF community. This conversation goes deep into the technology behind eBPF, what it is, why it matters, and how it's changing the way we think about networking, observability, and security in modern cloud-native environments.
We will also dig into how projects like Cilium and Tetragon are helping teams turn kernel-level power into real-world capabilities. This will be a bit of a technical episode, yet still accessible, whether you're already working in this space or just trying to understand why eBPF has become such a big deal.
Let's welcome Liz Rice, Director of Software Engineering at Isovalent. Hi, Liz.
Hi, Liz.
Hi, I'm good. Thanks for having me.
It's cool. It's cool to have you. Do you mind introducing yourself a little bit for those who haven't had the chance to meet you before?
Sure. Yes. So my name's Liz Rice. I am an engineer by, background. I run what we call the community team and the technical mindshare team at Isovalent. Isovalent is now part of Cisco. We were acquired a couple of years ago thanks to our eBPF technology, which we're going to talk about today, and some of the things that we built on top of it, like Cilium, which is really the default networking solution for Kubernetes. And then that's a whole other side of what I do. I've been involved in the kind of cloud native Kubernetes space for a very long time. So I do things like sit on the governing board for the Cloud Native Computing Foundation. I hope that gives you a very, very quick whistle-stop tour of who I am.
Actually, while researching a little bit on your background and things like that before the show, I came across your website, lizrice.com, and there was something that caught my attention. On your bio page, there is something like, ask me about that time I lost a laptop in a taxi, and now I'm curious about it. So,
It was definitely a lesson in why you need to have backups and what your disaster recovery plan is. So while I was a student, I was actually a student at an engineering school in Paris. And I had a kind of part-time job on the side it was essentially scripting for like SQL Server. I was building this whole system for, presenting some information. And the person who'd commissioned me to do it rang me up one day and said, could you come and present this to like a team of really senior people from the company that I was doing it from? And I was like, okay. I'm 19 at this point, and I'm going to have to present this in French, which is not my first language. So I prepare the whole thing, and they've actually lent me a laptop to do this work because I'm old enough that students wouldn't necessarily have their own computers, and they lent me this laptop. And I was all ready to go, and I'd had to do a lot of work to get it to the point where it was ready to present. I'd asked what's the best way to get to the site. They said, get a taxi. I got a taxi. I got out of the taxi, and then I wondered where I'd put that laptop. And I was literally checking my pockets. Like, what have I done with the laptop? And obviously I'd left it in the taxi. So I had to go to this presentation, essentially deliver my solution by acting it out, really. It was just terrible. And the lesson about backups was I had not taken a backup for about a week. So I had to redo all the last week's worth of work, and it was terrible. I was so embarrassed. So after that, much, much better at taking regular backups of my work.
yeah, you learned it the hard way, I guess.
Yeah.
All right. Thanks. Well, it's great to have you. Maybe to kick off our conversation, we will mostly talk, I think, about eBPF. And most people heard about BPF from the original story of eBPF, which came from TCP dump, Wireshark, and the Berkeley packet filter thing. But it's today much more than that. Can you walk us through where it came from, where it is today, and what's the future of eBPF?
Yeah, so I'll give you a quick summary of it, and I will also recommend that if people really want to dig into this, they can watch eBPF documentary. If you go to eBPFdocumentary.com, incredibly well produced movie about how eBPF came to be and why, and you get to meet all of the key players, including people like Thomas Graf and Daniel Borkman, who are part of the isovalent team. So BPF originally stood for Berkeley Packet Filter, but that was really confusing people because eBPF can do more than just filtering packets. So forget that it ever stood for Berkeley Packet Filter. Just think of it as a standalone term, eBPF. What it allows us to do is to write bespoke programs that we can load into the kernel and change the way the kernel behaves dynamically. We can have bespoke programs to do different things in different circumstances. Individuals can write their own eBPF programs, or they can have bespoke policies rolled out to individual machines based on dynamic eBPF programs. And essentially the very first seed of the idea came from Alexei Starovoitov, who was at PlumGrid at the time. And he was essentially struggling with some compiler bugs. He was like, if I could control what was going on in the kernel, I wouldn't have to worry about these kind of compiler errors that he was having. And he put a proposal for essentially programmable, making running dynamic programs in the kernel. And it was a bit of a giant idea that the kernel mailing list, the kernel maintainers were not super enthusiastic about. But Daniel Borkman saw it and said, I think there is something really interesting here. So Daniel and Alexei put their heads together, thought about how could they take this idea of dynamic programs within the kernel and kind of make it acceptable. They hit on the idea of extending Berkeley packet filters. So those already existed. They allowed you to take a network packet and run some code on it or triggered by that packet. And they had this idea, well, what if it could be a bit more general purpose? Could we attach this to other events in the kernel? And essentially what they came up with is the ability to dynamically change the way your kernel behaves. So you can load an eBPF program into the kernel, attach it to all kinds of different events and run programs. Those programs can observe what's happening in the kernel. They can even potentially change what's happening in the kernel. If it's a network packet, they can modify the contents of the network packet or maybe even drop it on the floor. But because we can do so much more than just packet filtering, we can hook into literally pretty much anywhere in the whole kernel. For that reason, we don't call it Berkeley packet filtering. It used to stand for extended Berkeley packet filtering. We now just consider it a standalone term. It's just eBPF, because so many people were getting confused about, surely this is all just to do with networking and packet filtering. Actually, no, we can do a lot more with it.
So you can intercept like process calls, files being written, any kind of activity in the kernel can be intercepted, right?
Yeah, absolutely. In fact, you can also hook eBPF programs to user space, but you don't necessarily know what applications are running in user space, whereas you have a pretty solid idea for a given version of the kernel. You know what that kernel is going to have in it. So you can attach to file access, memory access, network access. There's an amazing diagram that was produced really quite early on where there was a project called BCC, and it has a whole load of different command line tools written using eBPF to monitor and give you statistics about all kinds of things that could be happening in your system. And the really nice thing about this diagram is it just gives you a good illustration of so many different places that you can hook eBPF into. It's a bit of a frightening diagram when you first see it, because you know, there's no way you're going to memorize all of these different command line tools. But just to give a sense of all these different aspects of the system and how we can use eBPF to inspect what's going on and maybe even modify what's going on.
That sounds very powerful, but isn't it a bit risky? Because you said like you can intercept a packet and run some code to check it. What if your code takes like forever to execute? So you intercept way too much stuff and you run code forever, you could stop the system, right? Like that sounds dangerous to me.
So one of the incredible inventions that make eBPF so powerful is a thing called the verifier. When you load a program into the kernel, it first has to pass this verification step, which is really analyzing all the possible paths through that program and ensuring that it cannot crash, because crashing a kernel is a really bad idea. It's going to bring down that computer. And it also ensures that it will run to completion within a reasonable amount of time, that amount of time actually being dictated by a number of instructions. So we can ensure that BPF programs are always safe to run, they're always going to complete within a reasonably short period of time. But then we can also chain them together and do really, really complex things with them these days.
What's the magic with the verifier? I mean, how can it detect correctly that the program is safe to run and will not crash, will not cause any memory problems, will not try to read a pointer that points to dev null?
As the verifier runs through the program, it's keeping track of the state of a number of registers. eBPF programs, they're typically written in C code, which then gets compiled into eBPF bytecode. And those bytecode instructions look really similar to machine code instructions. So they're typically, load a value into a register, or add these two registers together, or on a certain condition, jump to a different instruction. So if you've ever come across any machine code, then looking at eBPF bytecode looks really similar to that. And the verifier is essentially stepping through those programs, keeping track of the states of these different registers, also keeping track of the type of thing that it thinks is in a register. So if it's got a memory address, it knows that it's a memory address. Or if we use a thing called maps to hold data. They're kind of data structures that can be shared between eBPF programs and user space. And so we might know that a particular register has got a value from a map, or that it's the key into a key value store. By keeping track of what type of memory it is and what the possible values for that register might be, it can figure out, are you asking me to jump to an address, and that address is a program instruction pointer, but it might not be, because that isn't the right kind of memory that's been stored in that register. It can essentially reject if you're trying to use a register value in the wrong way. If you really like going into the details, you can get the verifier to output essentially what it's thinking at all stages. It can kind of show you what type it thinks each register is holding and what the possible ranges can be. So, for example, if you tried to do a loop, in the olden days, loops were not allowed in eBPF programs. They are allowed now, but the verifier will be looking at, well, if you're asking me to do this 1,000 times and there's more than 1,000 instructions, then I know I will blow the 1,000,000 instruction limit, which it currently allows. There's all sorts of really clever optimizations in the verifier as well to essentially, if you have the same state at the same time, it knows, well, okay, I've been here before, I don't need to analyze this path again. So this analysis happens at the point where you load the program, and then you can run it any number of times. So it's only done once as you're loading the program into the kernel.
Yeah, I've had some bad experience with it when I was practicing in the beginning. Like you try to load something and it's like, no, I'm not going to run that because it's going to crash. So
Yeah,
it's actually clever. Good at figuring out things that that would indeed lead to a big problem. So it's quite intelligent in that matter. And I wish we had that for normal programs, telling you, okay, it's going to crash, be careful.
I imagine there are a ton of like Rust programmers screaming right now, like, just use Rust. That's what Rust does.
I had Rust in my list of questions. So we hear Microsoft even considering a lot of Rust now in their Windows operating system. Rust is getting everywhere for safety reasons. What about eBPF? I've heard a lot of C, but is it moving to Rust, or what is the interaction there?
Yeah, the Rust compiler supports compiling eBPF bytecode from Rust instructions. So that is another path that you have these days for creating your eBPF code. I'm not a Rust expert, although the language that you compile from C into eBPF code, it is C, but sometimes we call it restricted C because you can't do everything in eBPF that you can do in C. And for example, you have to do things like every time you want to dereference a pointer, you have to explicitly check that it is not null. And that's how the verifier will know, okay, I know this isn't null because you've just checked it. So therefore, it's safe to dereference that.
So there is no real need of Rust, right? Because it's already very restricted and limited. So like you can do it with Rust, but there's no major visible advantage because
if you're a Rust programmer and you know what you're doing
You're
with
more
Rust,
used to it.
then that makes sense. You don't need to learn a whole new language if you're already familiar with Rust. And vice versa, if you're a C programmer, you don't need to learn Rust to do eBPF programming. And fortunately, none of us have to write eBPF bytecode by hand.
Who would enjoy that? I'm sure some people would, but
There are blog posts out there where people have done it.
now that we've spoken about the things that you cannot do with eBPF, or thanks to the verifier, what can we do with eBPF? What are the things that it enables you to do much better than if it didn't exist?
So the classic trifecta here is networking, observability, and security. I think all of the things that it's really great at are things where the kernel is involved already. And we can change the kernel's behavior either to optimize it for a particular circumstance or to do security. I think maybe it's even worth just diving in a little bit into what we're talking about when we talk about the kernel of an operating system. So the kernel is the part that really does interfacing with hardware. And a lot of developers are writing applications. Those applications might be sending and receiving messages over the network or reading data out of files. And unbeknownst to those application developers, the language they're writing, they might be writing in Rust or Python or whatever they're writing in. That application code isn't directly sending the network message or reading the file. It's actually making what we call a system call to ask the kernel to do it on behalf of the application. And the kernel's involved in all of these things that touch hardware or even sort of virtual hardware. Files, network, memory. It's also coordinating different processes. It's checking permissions. All of these things are really interesting from a security point of view. If we think about what would an attacker want to do? They might want to read data from a file that they're not entitled to. They might want to write files that they're not entitled to. They might want to contact network addresses that they shouldn't be contacting. They might want to escalate privileges. Again, something that the kernel is involved in. Therefore, the kernel is a really great place to have policy checks that say, should this file access or network access or privilege change, should this actually be allowed or not? So being able to dynamically change the way the kernel behaves allows us to do these really fine-grained security controls. Maybe I'm going to say you're only allowed to access this file on a Tuesday. We could do that. That would be fine. We can be very specific about exactly which processes can perform certain operations. We can also do really cool things with networking. One of the things that the iSurveillance team originally created was a networking project called Cilium, and it enables much more efficient container networking because we can essentially sidestep, we can shortcut some of the paths that network packets would otherwise have to go through to get from a physical network interface into a container, say.
Before we deep dive into Cilium, I would like to spend some time on it. Is it fair to say that for every syscall that exists, there is an eBPF hook that can be, plugged into if you want your eBPF program, or is it not a one-to-one mapping today?
So you could hook into every single syscall. That's certainly possible. It's also possible to hook into any trace point in the kernel. You can hook into any function in the kernel. You can actually hook into function plus offsets if you happen to know what they are. You can hook into points in the network stack. There are good reasons not to hook into syscalls, particularly for security tooling. There's something called a time of check to time of use vulnerability, where when you're making a system call, your application code has to write some values into CPU registers, and the kernel is then going to read those values back out again. If you attach an eBPF program kind of in between those two states, it's possible for the eBPF program to read values that the user space application wrote. A malicious user might have a small window of opportunity to change them before the kernel then reads them. So for that reason, the system call interface is not considered a security interface. There's actually a comment somewhere in the Linux code base to say, don't treat this as a security interface. For that reason, a lot of security tooling, well, particularly Tetragon, will hook further into the kernel. There's a series of functions or an API, if you like, that's called the Linux Security Module API. So it's function calls within the kernel where you might make checks to say things like, is this file access permitted? We're about to open a socket. Is that okay? Those hooks are much more appropriate for security tooling. If what you're trying to do is count the number of times that a syscall's been called or get other kind of performance information, then a syscall could be a perfectly legitimate place to hook in. But it's by no means the only place that you can hook into.
And still on the security aspect, as every feature, this can be used by the blue team as well as by the red team. So the good guys versus the bad guys. So what prevents threat actors, adversaries to use eBPF in their programs, in their hacks, just to also take advantage of the fact that they have control of everything in that location?
Yeah, for sure. In the wrong hands, eBPF could be very dangerous. When an eBPF program is being loaded, it needs permissions. So depending on how detailed you want to get, we can say it needs root access, or we can say actually it needs some Linux capabilities called cat BPF and a couple of other, depending on the type of program. Essentially, we can say root users can load BPF programs. You don't want anybody having access to BPF that you wouldn't otherwise give root access. In a lot of cases, if somebody was able to load a malicious BPF program, then they were able to do a whole load of other bad things on the system. Now, of course, you might have a legitimate user or a legitimate process inadvertently loading malicious eBPF. One thing you can do is have an eBPF program policing whether or not other programs are allowed to load BPF programs. So at least being able to detect when another BPF program has been loaded by a different process. So that's one really great way of detecting what's going on.
I'm afraid that this will become like a bloatware of eBPF application, if you want, because everybody will make their own BPF stuff and it will just become so big that you would not even know what's happening there anymore. What's your take on that?
Okay, so I guess first of all, writing BPF programs is not easy, and there are many cases where BPF would not be the right hammer for any given nail. We've proven that eBPF can be Turing complete. So in theory, you could write anything you like. In practice, it's not necessarily a good idea. So there will be lots of things that could be written in eBPF, but just nobody will because it's a bad idea. In terms of the sensible applications of eBPF, like networking and observability and security and performance monitoring and so on, there is at least a theoretical danger of too many BPF processes trying to hook into the same event, gone on to help coordinate those different BPF programs and understand the sequence in which they need to be executed. Have two things that are tracking the same event. You want to know what's the correct ordering for those two programs to be triggered. And we also, in the real world, we do see people saying, well, how can I run this project and that project at the same time when those two projects are trying to achieve the same thing? And really the answer is don't. Why would you do that? That's a silly thing to do. You're just asking for trouble.
It's a bit like if you wanted to run 2 antiviruses on your computer at the same time. That would simply not work, right? You would have a lot of troubles with that.
Yes. Yes, it's exactly the same kind of thing.
I have a question about security. So I am not very well versed into how anti-malware and antivirus work, but it feels like they should use eBPF if they don't already. And without naming brands, there's a few famous ones that have crashed thousands of computers recently in the previous years. Would eBPF and having a safe way to do kernel activity without being in the kernel be a solution to that? Or am I completely misunderstanding?
No, you're exactly right. And the infamous case, I guess it's coming up for about 2 years ago, where there were a lot of blue screens in a lot of airports around the world. That was a really good illustration of why you do not want your kernel to crash. And that certainly did, open up a few more conversations around how eBPF can be used to detect the same as a safe way to build these tools that can detect malicious security events. And certainly because of the verifier, you cannot end up in that, blue screen of death scenario. I should probably say, eBPF came from the world of Linux, but there is now eBPF for Windows. Our team have been working on that hand in hand with Microsoft to be able to build things like security tooling on Windows as well. It's definitely being recognized as a good way to avoid that kind of scenario.
We have this tool called Tetragon. Do you mind explaining us what it is and what's behind the name?
Yeah, so Tetragon is a security tool, a runtime security tool, and it uses eBPF to enforce policies that, well, first of all, allow us to observe interesting security events, like, for example, file access or network connections and so on. It allows us to understand not just which process caused an event, but how the process hierarchy that led to that event. And we can also optionally enforce policies so we can prevent certain events that we've defined as being malicious. So we might, for example, prevent certain users from accessing certain files, but we can be more granular than your traditional permissions on the machine. We might say, well, these users are only allowed to access those files on a given day of the week or something like that. We can be very specific about network. We can allow certain processes to perform certain operations while other processes are not allowed. And we can also detect things that are very likely to be malicious, for example, changes in permissions and privilege escalations, that kind of thing that you really want to be aware of. With Tetragon, we can detect these events and send them to a SIEM or send them to a Splunk. And because they've got all this detailed information about what process had triggered it, and, for example, everything that had led up to a network connection being attempted, for example, that's super useful for forensics to be able to understand how a malicious event or a potentially malicious event had come to be. Oh, you also asked about how the name came about, which is quite fun. So there's I guess, first of all, logo for eBPF is a B. So the EB, in fact, the official name is EB for the B. And you'll see a lot of Bs around, everything to do with eBPF. And there is a type of B whose Latin name, the second part of it is Tetragonista. And it's basically considered harmless to humans, and it produces lots of honey. That seemed like quite a nice kind of name to derive our security tool name from.
Okay. And I have a more networking related question. So eBPF is for calls that are made on the control plane, right, towards the CPU. Talking about network traffic, you cannot do that with fastpath data plane. Because my question was, is that going to come into play for AI workload where you have to pass 800 gigabits of traffic? I guess not, right? Because you cannot stop and do any processing on those packets, right?
Correct. So if you're talking about, for example, all of the traffic going through a network switch where there may well be a CPU or DPU that can run eBPF, and as you say, that's being used for the control plane. So that's typically what you would do we have this in Live Protect, which is being rolled out to some Cisco smart switches, where the eBPF is not there to inspect the traffic because, as you say, that's on a fast data plane. But the eBPF is there to allow rolling out security controls for known vulnerabilities in the control plane in the network stack. So, for example, say there's a known vulnerability in your BGP stack that's running on a particular hardware device. You don't necessarily want to patch the switch because you'd have to bring down all the traffic and you'd have to redo all the BGP peering, but you can dynamically roll out a shield, live protect shield, to mitigate that vulnerability dynamically without affecting any traffic. As you say, it's only affecting the control plane, and it allows you to then think about rolling out the patch or the upgrade at a convenient time.
When you're talking about known vulnerabilities, I think it's misleading to network engineers who, are used to, you have to wait for a patch and then we install the patch and it takes time. I think eBPF makes it work for even any future vulnerability, but of course we need to be aware of it and know its signature, right? Because when you know the signature, then you can write the eBPF signature to detect the call, the escalation, the whatever you need to block to prevent the attack to be successful, right? So once the signature is known, you can block attacks even if they're brand new without installing a patch. Am I getting it right?
Yeah, that's right. You're rolling out a policy which is really kind of translates into eBPF programs and data for eBPF programs. Yeah.
But does Live Protect need the operating system to be rewritten a lot with eBPF in mind? Or potentially like a lot of Cisco iOS XE can already be implemented with it?
eBPF is a subsystem in the Linux kernel. And so long as the Linux kernel you're using is recent enough, then it will have eBPF capabilities that mean you can then load your eBPF program into it. If the kernel is recent enough and has eBPF enabled, it's part of the kernel configuration, whether it's available or not. Increasingly, modern kernels do have eBPF support. It's been around now for 10 years, so we're really seeing a lot of application servers and kind of application operating systems now really support it pretty much universally, but also hardware operating systems if they're Linux based.
Is it time for Cilium?
Go ahead.
You mentioned in the beginning that one of the major projects that you are working on is Cilium, so container networking. Do you mind giving us a high-level introduction of why is it important to have this type of project in the kernel compared to the other container networking project that exists?
So let's start by just thinking a little bit about container networking. So we take an application, we put it in a container, and that container is intended to deliberately isolate the application and all its dependencies from the host that it's running on. Now, as part of that isolation, it gets essentially its own copy of the networking stack. It's called a networking namespace. And the networking namespace is connected using a virtual Ethernet connection to the networking stack on the host. And for a packet to leave the container, the application wants to send a packet, it has to traverse the networking stack in the container's networking namespace, goes across the virtual Ethernet connection, has to be kind of received by the host networking namespace, which decides what to do with it. And it's typically going to be send it to another container, possibly on a different machine, which means it's then going to go through the network namespace on host again. Essentially, we've got this extra network hop between the host and the container. And if you look at kind of traditional container networking, you'll see additional latency and a performance hit just from running your applications in a container. With eBPF, we can be a lot more smart about that kind of extra hop. So, for example, when a packet arrives on the network interface into the server, we can use an eBPF program to inspect it, look at the destination IP address. In Cilium, we're keeping track of different containers or Kubernetes pods, and we can take that packet and insert it directly into the container's networking namespace. So it avoids going through the stack, that extra hop. And until recently, we were less able to do the same thing outbound because we couldn't hook eBPF programs inside the container network namespace. But quite recently, this is Daniel Borkman in our team put some enhancements into eBPF called NetKit that do allow us to extract those eBPF packets from within the container network namespace. So we can do this kind of shortcutting for packets, both ingress and egress. And the net result of this is no performance overhead in container networking. You get networking traffic flowing just as quickly, whether it's to a containerized application or just to an application running directly on the host. And kind of eliminating that container overhead is a huge win. So that's the performance side. Then there's also the security side, that while we're hooking into these packets to figure out where they should go, we can also be hooking in to see, should this connection even be permitted? And Cilium keeps track of the identity of different Kubernetes pods, and those pods have labels that say what kind of workload it is, what the application is. And we can use those labels to allow the user to build policies that say my front end application is allowed to talk to the back end application, but it's not allowed to talk directly to the payment gateway. And so we can have these network policies that can be executed incredibly efficiently by eBPF programs, inspecting packets and making very quick decisions about whether to pass on the packet or, like a firewall, drop packets that are out of policy.
Cool. So mostly more flexibility in the way you do security, because you have like granularity on the type of applications. So it's like a layer 7 decision that influence your networking stack at lower level. And thanks to eBPF, it's much faster than doing it the old way, which was with additional hops through the kernel layer. Is my understanding correct?
So one subtlety there is we can do layer 3, layer 4 purely in eBPF. I should probably drill down into why we have to do this in dynamic policies. In cloud native, in Kubernetes, we might have, rather than having one instance of an application running, we might be running a variable number depending on demand. So applications will scale up and down with additional pods being created. And those pods get allocated an IP address. So they're kind of coming and going dynamically. They might be scheduled on any machine in a cluster, and there's no relationship between the IP address and the functionality of the application. So in traditional networking, you might say this IP address and this port means it is, let's say, front end. In the Kubernetes world, you can no longer do that. The IP address might get reused in 5 minutes time. But with Cilium, we can keep track of the identity that's associated with the IP address at any given time. We know what application is running in each pod. We've got these labels that identify the workload. So although we can see the IP addresses, the reality is we know what that relates to in terms of the application. So we can have these network policies that are able to keep up with this dynamic nature of how applications are distributed in Kubernetes. We can also do layer 7 network policies where we can, for example, allow HTTP gets but not HTTP posts or something like that, or we allow network connections to certain DNS names. And we actually make use of a project called Envoy to do that layer 7 inspection. So we can very efficiently call out to Envoy when we need to get that layer 7 inspection.
If you look at Kubernetes clusters, they are deployed on several nodes. How does the eBPF policies in Cilium are synced between the different nodes? Like, because you might have a container on one side and another one on the other.
It's both, essentially. And it's really how Cilium interacts with Kubernetes. So Kubernetes is going to schedule a pod, so as in decide which node that pod is going to run on. And as the pod is created, it's going to get assigned an IP address. Cilium is going to be involved because there needs to be networking set up for that pod. So the Cilium agent locally on that node knows about it. But the Kubernetes API also knows about it, and essentially it distributes knowledge about that pod across the cluster. So Cilium endpoints can very quickly kind of catch up with how these pods have been distributed. We can also embed the identity information into network packets so that the receiving end knows the identity of the pod that sent that packet.
Is that using an extra network header, or are you reusing one of the feed like DSCP?
Yeah, and we're definitely getting to the limits of my detailed knowledge of Cilium, because there are some different networking modes where there are overlay modes or kind of native routing modes, and depending on the different mode, we can or can't insert the identity into the header.
Okay, thank you. I'm just gonna pause for a minute and let Nico. Nico, if you have a question.
I wanted to completely switch and talk about open source. What is the benefit of open sourcing all of this? I mean, first of all, yeah, you said eBPF is not an invention of Cisco or Isovalent, but why do we stay in the open source so much? Because we're giving all competitors, the same tools we're using.
Yeah, so I think in these days, open source is really one of the ways that standards are created. Really good example would be Kubernetes itself, Docker also, how people run containers. It's all based on open source. And people have come to expect that infrastructure components will be built using open source. Now, just because you can run, you can use Cilium, you can use the open source distribution of Cilium very effectively in, pretty highly scaled environments, and people do. But open source is free the same way that a puppy can be free. I can give you a puppy, it's at no cost to you, but you're still going to have to feed it, you're going to have to take it for walks, you're going to have to pick up after it. There will be ongoing costs associated with that puppy. And the same is true for open source. So organizations that are either not using it in very stressful environments, if it's not mission critical, fine, okay. But if it is being used for mission critical workloads, you're either going to have to invest in people who can help you out with the deployment of it in the first place, helping you out when anything goes wrong, helping you sort of design how it's interacting with the other components in your network. Or you can come to Cisco, you can come to Isovalent and get that expertise. And particularly when we think about things like how is your Kubernetes networking going to interact with your traditional networking and your, multiple data centers and your geographic distribution, things can start to get really complicated. How is it going to interact with your existing virtual machine workloads? How is network policy going to be distributed across your Kubernetes cluster and your traditional workloads? All these things require, expertise. You don't magically get someone to come and solve your kind of whole networking problem if you just use the open source components. So, and the same is true for Kubernetes itself. You can run Kubernetes from the vanilla open source distro. Most people are actually running a managed Kubernetes service, or they're going to a public cloud provider and using that managed Kubernetes offering.
Okay, thanks again for joining us today on this episode. If people want to learn more about eBPF, Isovalent, and all the projects that you're working on, where can they find documentation?
Yeah, sure. So isovalent.com has lots of information about the products that we build, but we'll also take you to lots of other resources, including books that you can download. My book on learning eBPF, if people want to download that, they can. There's also a ton of interactive labs that you can find on the Isovalent website. So if you want to play with eBPF or Cilium or Tetragon, try it out for yourself, then it's a nice, safe environment for learning about that. And you can also find lots of information on eBPF.io, which is the technology website, or Cilium.io if you're interested in the Cilium project.
And don't forget to watch the eBPF documentary.
Absolutely.
Or also Cisco Live, where you have a presentation, right? I typed Liz Rice before this interview, and your presentation was very clear also and very accessible.
Fantastic. Good. Yes.
Amazing. Thank you. Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us by searching for the channel called Cisco Tech Stories on your favorite podcasting app. We're also present on the Cisco Podcast Network channel, where you can discover other podcasts from Cisco. Feel free to leave us comments or questions on Spotify. Thanks, and see you next month.
Little watch the traffic pass.